Okay, so we are still in chapter 7 and talking about complex numbers. So just a little refresher from before break. Remember, we talked about representing complex numbers in the complex plane. So where we have a two-dimensional plane, the horizontal axis is referred to as the real axis, and then the vertical axis is referred to as the imaginary axis. And a complex number in rectangular form would have horizontal component A and vertical component B. And that point could represent the number A plus BI. Okay, so A plus BI is in rectangular form. Now, this complex number, we say has a modulus, or magnitude, which is the distance from the origin to the point. And we call that R. And then it also has direction, which we'll call angle theta. So A plus BI can also be represented in what we call polar form, which is R times cosine theta plus I sine theta. And you can go back and forth between the two. So we're first going to look at finding the product of two complex numbers. So if you're multiplying a complex number that's in polar form by another complex number that's in polar form, you can use this kind of formula for finding the product, where basically you multiply the magnitudes and you add the arguments. In class, I derived this, but I will send you guys the notes that has the derivation. If you have any questions, I'm happy to explain it to you. But just so that this video isn't super long, I don't really want to derive all of the products and quotients for complex numbers. Now, if a complex number is in rectangular form, so let's make a note. That you can multiply complex numbers in rectangular form using the distributive property. Okay, but if you're given two complex numbers that are in polar form, and especially if the angles for the complex number is not an angle on the unit circle where you can't simplify exactly to find A plus BI, then the formula up here works best. But let's say that you had to multiply, 2 plus 3i times 3 plus 2i. Then you can just use the distributive property, right? So 2 times 3 is 6. 2 times 2i would be plus 4i. 3i times 3 would be plus 9i. And then 3i times 2i, well, I times I is negative 1, so that will actually be minus 6. Oh, so this ends up being equal to 13i, pure imaginary number. Now to find, let's do an example where we're actually finding the product. So if we want to find z1 times z2, the product of these two complex numbers, we're going to multiply their magnitudes, and then we're going to add their angles. So when we simplify, that'll be cosine of 120 degrees plus I sine of 120 degrees. Okay, so this is polar form. But we also want to represent the product in rectangular form. So remember, to go from polar to rectangular form, you can just simplify. So cosine of 120 degrees is negative 1/2. And sine of 120 degrees is root 3 over 2. And then when we distribute the 10 in, we'll get negative 5 plus I times 5 root 3. So this is the product in rectangular form. Okay, so we can also find the quotient of two complex numbers that are in polar form. Again, the notes that I'm sharing with you will have the derivations on it, but for the sake of time, I'm not going to include those in this video. Now, if you were trying to divide two complex numbers that were in rectangular form, for example, if you wanted to do like 2 plus 5i divided by 3 minus I, you could multiply by a version of 1, which is the complex conjugate of the denominator over itself, and then distribute that out. That'll make the denominator real, and then you can simplify it to get that complex number. Okay, but for two complex numbers that are in polar form, you divide the magnitudes and subtract the angles. Okay, so here if we want to find z1 divided by z2, that'll be 10 divided by 5. And cosine of 275 degrees minus 65 degrees plus I sine 275 degrees minus 65 degrees. Okay, so we can simplify. So that'll be 2 cosine of 210 degrees plus I sine of 210 degrees. Okay, so that's the quotient in polar form. And then for rectangular form, we can just simplify. So cosine of 210 degrees will be negative root 3 over 2. And then sine of 210 degrees is negative 1/2. So it'll be negative root 3 when we distribute the 2 minus I. Okay, so that's the quotient in rectangular form. And just a note, if theta is negative or greater than or equal to 360 or 2 pi, find the coterminal angle on the interval between 0 degrees and 360 or 0 and 2 pi if you're in radians. Okay, so for finding the powers of complex numbers, like let's think about just squaring the general form of a complex number, which is r times cosine theta plus I sine theta. So that would be r squared, right? So magnitude times itself. And then it would be cosine theta plus I sine theta times itself. I'm going to write it out like this for us to expand. So if we were to distribute cosine, we'll get cosine squared theta and then plus I times 2 sine theta cosine theta, and I times I will be negative 1, so that'll be minus sine squared theta. I'm just thinking about multiplying this out. And then if I rearrange this, I'll have cosine squared theta plus I times sine, times 2 sine theta cosine theta. Oh no, I meant to rearrange that. Sorry. Cosine squared theta minus sine squared theta, and I can rearrange the terms by the commutative property of addition. Okay, so we still have r squared here. Now cosine squared minus sine squared, that's an identity. That's double angle identity for cosine. And 2 sine times cosine theta is the double angle identity for sine. Okay, so z squared is r squared times cosine 2 theta plus I sine 2 theta. Now if we wanted to find z cubed is going to be the same as z squared times z. So we'll have r cubed, because r squared times r is r cubed, and then we'll have the rest, so cosine 2 theta plus I sine 2 theta times cosine theta plus I sine theta. And if we multiply that out, we'll have cosine 2 theta times cosine theta plus I times cosine 2 theta sine theta, plus I sine 2 theta cosine theta. Let me give myself a little more room. And then that'll be minus sine 2 theta sine theta. And if we do a little rearranging again, we'll have cosine 2 theta cosine theta minus sine 2 theta times sine theta. And if I factor an I out, that'll be cosine 2 theta sine theta plus sine 2 theta cosine theta. Okay, so now thinking back to our identities, this is actually the sum identity for cosine. So that would be cosine of 2 theta plus theta. And this is actually the angle sum identity for sine. And when we simplify that, I'm going to give myself a little more room. We simplify that, that's going to be r cubed cosine 3 theta plus I sine 3 theta. So we could probably guess what like z to the 4th would be. It would be r to the 4th cosine 4 theta plus I sine 4 theta. Okay, now this pattern can be seen in de Moivre's theorem. So basically, if you're trying to raise a complex number to a power, you can use de Moivre's theorem if the complex number is in polar form. Now, if you have a complex number that's in rectangular form, like let's say that we wanted to find 1 plus root 3i to the 12th power. That would be really hard to find. You would have to multiply out 1 plus root 3i times itself 12 times using the distributive property, and it would be kind of ridiculous. But now with de Moivre's theorem, if you rewrite the complex number in polar form, you can actually just apply this theorem and easily find 1 plus root 3i raised to the 12th power. You can always simplify then to get the complex number back into rectangular form if necessary. So in this example, is that the exact number I put? Oh, that's funny. Okay, but to the 10th power, not the 12th power. So we're going to first rewrite the complex number z in polar form. So to do that, we're going to sketch in the complex plane. Okay, so I need r and I need theta. R I can find by taking the square root of a squared plus b squared, so 1 squared plus root 3 squared. So we get 2 for r, the modulus. And then we can use the fact that tan theta would be equal to root 3 over 1. And since we're in quadrant 1, theta has to be equal to pi over 3. So 1 plus I root 3 raised to the 10th power is going to be equal to 2 times cosine of pi over 3 plus I sine of pi over 3 raised to the 10th power. Now, if we apply De Moivre's theorem, that's 2 to the 10th then cosine of 10 times pi over 3, so 10 pi over 3. Okay, 2 to the 10th is 1024. And let's find the coterminal angle between 0 and 2 pi for 10 pi over 3, because 10 pi over 3 is over 1 rotation. So if we subtract 2 pi, which would be subtracting 6 pi over 3, we end up with 4 pi over 3. Okay, so this is 1 plus I root 3 raised to the 10th power in polar form. And why don't we simplify to also look at it in rectangular form. So cosine of 4 pi over 3 would be negative 1/2. Sine of 4 pi over 3 is negative root 3 over 2. So distributing 1024 in, that'll be minus 512. And then minus I times 512 root 3. So there's our answer in rectangular form. Okay, so for finding the roots of complex numbers, I want to start by giving you guys the equation x cubed equals to 1. Now looking at that, you will go, oh, x has to be equal to 1. But that's finding the solutions within the real number system. Actually, thinking back to like the beginning of the year when we solved polynomial equations for the roots of polynomials, we know that by the fundamental theorem of algebra, there are 3 complex solutions or roots to this equation. Remember, quadratics have 2 complex solutions, quartics have 4 complex solutions, not necessarily distinct solutions. You might have repeated roots. Remember, where the multiplicity is a number greater than 1. But you have the same number of complex solutions as the degree of the polynomial equation. And this is a third degree polynomial equation. Right, so x cubed equals to 1. So our real root, you would know, is x equals to 1. And it's important to point out that real numbers, remember, are complex numbers. It's just that we can think of, in this case, the value b, right? A plus bi is a complex number. B would be 0. So this would be 1 plus 0i. But we don't put the plus 0i in there. Okay, so it's a complex number, but it's also a real number, so we refer to it as the real solution or the real root. If I were to rewrite the equation as x cubed minus 1 equals to 0, we know that x minus 1 has to be a factor. And you either know what that factors to, you know the pattern that it factors to, or you could always use synthetic division. Remember, you put the coefficients, so 0, 0, negative 1, bring the 1 down. Okay, so x squared plus x plus 1 is the other factor. Now, this other factor here is an irreducible quadratic, and we refer to it as irreducible because it can't be factored over the real numbers. It can be factored over the complex numbers. So to see what the complex roots are, we have to actually use the quadratic formula. So x equals to negative 1 plus or minus square root b squared minus 4ac all over 2a. So we get x equals to negative 1 plus, that will be the square root of negative 3, which we can write as I times root 3. Or x is equal to negative 1 minus I root 3 over 2. So these are actually the complex roots. Uh-oh. Oh, there we go. These are our complex roots. Okay. Which they're complex numbers that actually have an imaginary part, other than 0. If the coefficient for I is 0, then it's a real number. So all of our roots are 1, negative 1 plus I root 3 over 2, and negative 1 minus I root 3 over 2. So these are the solutions to the equation x cubed equals to 1, meaning each of these numbers when raised to the third power will equal to 1. Right? If you take the cube root of 8, you tell me the cube root of 8 is 2. But there's actually, you're thinking to yourself, oh, well, what real number when raised to the third power would give you 8? But there's actually going to be 2 other complex numbers that when raised to the third power would give you 8. So we're going to be talking about finding the roots of these complex numbers. And again, I in class derived the nth root theorem, and it's in the notes. If you have questions about it, let me know. It looks complicated, but it's really not that bad. So we're going to treat k like an index. where k is going to be 0, 1, 2, so on up to n minus 1. So depending on the number of roots that you're trying to find for the complex number, it will determine the values of k. So we'll have r raised to 1 over n power times, and then that will be cosine of, that's really theta plus 2k pi divided by n plus I sine theta plus 2k pi over n. Now, I put the two formulas on here just to have the one with if the angle is in radians versus in degrees. Okay, so if we want to find the three distinct roots for 4 minus 4i root 3, I don't like how I have that written there. We are essentially trying to think, not think, but to find the three complex numbers that when raised to the third power will give us 4 minus 4i root 3. So we're finding the three distinct roots. We're solving this equation. So notice that in the nth root theorem, our complex number has to be in polar form. So we need to rewrite this number in polar form. So 4 and then negative 4 root 3. So we need r and theta. So r will end up being the square root of 4 squared plus negative 4 root 3 squared. Okay, so that is actually ends up being 8. Then tan theta equals to negative root 3. So theta is equal to 5 pi over 3. So this in polar form is 8 times cosine 5 pi over 3 plus I sine 5 pi over 3. So our first root, I'll use w sub 0. So that's going to be 8 to the 1/3, right? 8 to the 1 over n times cosine. It'll be 5 pi over 3 divided by n, which is 3, which is the same thing as multiplying 5 pi over 3 by 1/3. So we'll get 5 pi over 9. And k is 0 for the first root. Okay, cube root of 8 will be 2. I'm just going to leave this in polar form. Okay, the second root, I'm going to write as w sub 1. We'll still have a magnitude of 2. And if you look up here at the nth root theorem, we're adding 2k pi over n. So k is equal to 1 in this case, so it's 2 pi over n. So 2 pi divided by n will be 2 pi over 3. So I'm going to add 2 pi over 3 to the angle of the first root. So we get 2 times cosine of 11 pi over 9 plus I sine 11 pi over 9. And then the final root k will be 2. And if you look up here at the nth root theorem, if k is equal to 2, then that's plus 4 pi n, that's plus 4 pi over n. So plus 4 pi over 3, but that's the original angle of theta over n. So we could add 4 pi over 3 to 5 pi over 9, or we could just add another 2 pi over 3 to the angle in the previous root. So we could do cosine of 11 pi over 9 plus 2 pi over 3. And if our angles were in degrees, we could add 360 degrees divided by 3 until we had all the roots we needed. So that will be cosine of 17 pi over 9 plus I sine 17 pi over 9. So then we have our 3 roots. So basically, all three of these complex numbers, when raised to the third power, will be equal to this original complex number. We could do that. We could check that using de Moivre's theorem. Now, the question is also asking us to sketch the complex numbers in the complex plane, or complex roots in the complex plane. So let me draw my complex plane. Now, notice that each of these complex numbers has a magnitude of 2. So if I thought about sketching a circle centered at the origin, I'll do the best I can here. If I thought about sketching a circle centered at the origin that had a radius of 2, all of these roots will lie on this on the circle. So the first root has an angle of 5 pi over 9. Well, I know that pi over 2 is equivalent to 4.5 pi over 9, so it's going to be kind of just past in quadrant 2. And then 11 pi over 9, I know that 9 pi over 9 would be pi. Okay, so this one will kind of come out here in quadrant 3. And then 17 pi over 9 will be here. Now, if I draw some lines going to the origin, you could see, remember, we kept adding 2 pi over 3. So the angle between each of these roots is 2 pi over 3. And we could, if we were to connect each of the complex numbers, or the points that represent the complex numbers in the complex plane, we would actually have an equilateral triangle. Now, if we wanted to find the 4 roots of a complex number, we would end up with a square, or 5 roots. You can imagine 6 roots, 7 roots, and so on. But it'll always be the same angle between each of the roots because you're dividing 360 degrees or 2 pi by whatever n is. And I left off here to finish these final 2 examples in class, but it's the same idea using the nth root theorem.